All right, folks, this is the pre-lab for Lab 6, the randomization lab, which is about hypothesis testing. As always, I've sent out the R Markdown document via Canvas, so you'll need to download that onto your computer and then upload it to RStudio Cloud. I'm working locally on RStudio because I can make the font a little bit bigger, but all the code that I'm doing should work just the same on RStudio Cloud. So we're just going to start by loading our packages, like always, library mosaic and library GG formula. And then I can click the play button to run that code chunk. And what we're going to be doing in this lab is working to do some hypothesis testing. And we're going to think about the relationship between whether someone is self-employed or works for somebody else and the number of hours that they worked last week. So we want to know if there's a significant difference between those two groups and their working hours. So we could compute the observed sample statistic. I want to find the mean of the number of hours worked last week by self-emp or works for somebody, comma, data equals GSS. And these numbers look different to me. I've got, 38.8 something, 41.6 something. Those look pretty different. We could even use the diff function, so wrap diff around this whole mean piece of code to get the difference. So if I press play there, yep, it computes. It's like a 2.74 hour difference. Average difference. So that feels pretty big to me, but we're going to need to use statistics to be sure if this is statistically significant. So the first step to doing a hypothesis test is stating the hypotheses. And we can write them out in our Markdown using either words or notation. So if we were going to write this in notation using LaTeX, L-A-T-E-X, you don't pronounce it latex, it's LaTeX or LaTeX. And this is a notation format for math. If I want to have these big equations, I start with $2 signs and end with $2 signs. And then I can do things like h underscore 0, and that'll make an h with a little subscript 0, slash mu underscore, and then curly braces, all this stuff. And I've made this into a text format. If I took that off there, this would look all kind of funny and mathy. So I'm just going to put that text back there to make it look more like text and close off that curly brace. But if you don't want to mess around with that, you could have also just written the hypotheses out with words. Our null hypothesis, that's the boring thing. And we would say that, there's no difference in average number of hours worked by people who are self-employed and those who are employed by others. And our alternative hypothesis, that's the interesting thing that we're kind of secretly hoping is going to happen. So we'd say there is a difference in average number of hours. And then the way that we're going to do our hypothesis testing is we're going to build a randomization distribution. So the process of randomization is to look and see if you can simulate what the world would look like if the null hypothesis were true. So in this case, we want to ensure there's no relationship between whether someone is self-employed or not and the number of hours they worked. And we're going to do this by breaking the relationship between the two variables and mixing up the values of one of the variables. I have a YouTube video that I made for my lecture class that's more about the connection between Bootstrap and randomization distributions if you want to think about that some more. What we're going to do here is use the shuffle function, and we're going to shuffle to mix up the values of just one variable and leave the other one alone. So I'm going to make this new object called oneRandomization, and that's going to get, with the assignment operator, mean of number of hours worked last week, just like before, tilde, and then instead of just having self-employed or worked for somebody, I'm going to have shuffle of self-emp or works for somebody and still have data equal GSS. So if I control enter just on that line, nothing happens in my console, but I get a new thing up in my environment. And I could type, one_randomization to get it to print out the numbers. So I got 42.16 and 41.00. You probably got something different because shuffle works randomly. And I could ask the function diff to compute the difference for me. And so I found negative 1.15. So they're different, but maybe that could just be the result of chance. In fact, I know it's the result of chance because I ensured that by shuffling around the values of the self-emp or works for somebody variable. Because the shuffle is random, it's going to look different every time. This is just like the bootstrap sample, so we're going to do the same thing of setting our seed, and you might want to go and put this up in the top setup chunk of your document. That's probably the best place to have it. You only need it in one spot. And if you want to remember more about the seed, you could go back to my videos about the bootstrap. So just one randomization sample isn't going to do much for us. In order to make a distribution, we need to do the process many times, where many usually means at least 1,000. I think in the real lab, it asks you to do it 5,000 times. So here I'm going to make a new object called randomization, and that's going to get, with the assignment operator, the result of doing this 1,000 times. And what I'm going to do is the difference of the mean of, and then it's the same thing. We leave number of hours worked last week alone, but we shuffle the self-emp or works for somebody. So if I control enter on this, it takes a second because it has to do it 1,000 times, but it will eventually finish. And now I have a new thing in my environment, and I can click on it to look at it. So what this has is 1,000 observations of just one variable. This variable is being called someone.else. That's just kind of the automatic name that it came up with when it used that diff function to do the subtraction. And it looks like the first time I got a difference of negative 2.12, then 0.07, negative 0.85. So they're just kind of going back and forth, kind of randomly, negative and positive, all kind of around 0, but there's some variation. So this data set has 1,000 observations, the same number as the number of randomization samples we took, just one variable, the randomization statistic. And then we'd like to look at the distribution of that statistic. So we want to make a plot of that distribution. I think we're going to want a GF underscore histogram, parentheses, then we need the tilde, then we need the name of the variable. So in this case, it was called someone.else. So someone.else, comma, data equals, we need to think about which data set we want. We want the randomization data. And then if I control enter here, I get to see the distribution. And how is that distribution shaped? It is symmetric and bell-shaped, which makes sense because most sampling distributions are shaped like that. So if we just took one sample, that might be skewed, but if we have a sampling distribution, that's where we take a sample and then we compute a statistic and we record that statistic and we do that process many times, and then we build the distribution of statistics. That's almost always sort of bell-shaped and symmetric. And we'd be interested to know where that distribution is centered. So I could find the mean of the same thing, someone.else, comma, data is equal to randomization. And at least in my case, I found the mean was 0.008, which is almost 0. And does that make sense? Yes, it does, because the randomization distribution is always centered around the null value, which is 0 in this case. All right, so we want to get some evidence from this randomization distribution to either support or not support our null hypothesis. We could sort of use the 95% rule to kind of eyeball the middle of this distribution. I would kind of say negative 2.5 to 2.5, and so then anything that was less than negative 2.5 or greater than 2.5 would be pretty weird to see if the null hypothesis were true. So let's remember our observed statistic. That was the mean of, let's see, the number of hours worked last week, tilde self-emp or works for somebody. Data is GSS, and I'm going to put diff around the whole thing. Let's control enter. So that was 2.74. That would be, you know, kind of out here. That would be pretty weird just by eyeballing. But we'd like to have a p-value for how much of that distribution is as extreme or more extreme. And we can use the p-data function to tell us that. So let's do p-data. And then the first thing we need is a formula. So I'm going to do tilde. And this is going to be out of that randomization data set. So I'm going to put in the name of that one variable, someone.else. Then I need what the data is equal to. And in this case, it's randomization. And then the last thing that I need is what the Q is equal to. And in this case, it's our observed statistic of 2.74. And then I can control enter, and it'll tell me, you know, about 98% of the data is less than 2.74. So R is not actually giving you exactly what you want. It's saying most of the distribution is less than that, you know, to the left of that. But that's not the actual p-value. So in order to calculate the actual p-value, we want to do 1 minus that number. That would be the amount that is as extreme or more extreme. And then we actually want to multiply by 2 because we have a two-sided hypothesis test here. So our p-value is 0.044. And what do we conclude at an alpha equals 0.05 level? We reject the null hypothesis because, and I'll use a little LaTeX here, so I'm going to just do a single $sign for inline. 0.044 is less than 0.05. And then I could also do the conclusion in context to say we have evidence to support the idea that the mean number of working hours is different between self-employed people and those who work for someone else. And then the last thing is, how would this have changed if we were doing a one-sided test? Well, we just wouldn't have multiplied by 2. So I'm going to put that chunk down here. I'll just do that. So our p-value would have been smaller, so we would have had even more evidence against the null.